Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue with Class 18 on two-sample hypothesis testing. In the first video, I discussed reading in the dataset and making some plots. And in this video, we will discuss the actual hypothesis testing. So I've downloaded our Markdown file. I've downloaded the second dataset. You have the first dataset from a previous class. And in RStudio, I read the file in and I knitted it, and we are now looking at the HTML that resulted. So we're going to, last time I also talked about how to conduct the hypothesis test, the mechanics of the hypothesis test, which is review from the notes. And we've looked at all the data set for the handspan data. Okay. So let's start here today in this video. We want to know whether the females, this top one, this estimated mean, whether there's evidence that the sample of that the population of UNM students has a mean that's different than the population of people in the United States, adults in the United States. And then you will get to do this again for the males. So let's conduct the hypothesis test. So model example, that means I'm going to model this example. If you want help on the t-test function, you can do !t.test and learn more about that function. Okay, so we are ready to get started. The way I've done this is I wrote the code and to conduct the hypothesis test, whose output is here, and I've got even a plot that I produced from a function that I wrote that's in that ADA functions.r that you sourced at the beginning of the code to make a plot. And then this is where you would in the next example fill in the results for the hypothesis test. So just as we discussed at the beginning of last video for this hypothesis test, we're going to do these first 5 steps. We're going to set up the null and alternative hypotheses in words and notations, choose a significance level of alpha, compute the test statistic, determine which tails of the distribution correspond to the p-value that we're calculating, and maybe report the p-value here, and finally state the conclusion based on the relationship between the p-value and the alpha, whether you reject or fail to reject the null hypothesis. Okay, so all that is right here. Let's go through each step right here, and then we'll scroll up to look at the evidence from the testing code above as we need to. So the hypothesis here was test whether female height is equal to the U.S. average. Okay, so equal is the key part here. And I can't use my mouse correctly. There we go. Equal. You get it. All right, so I'm page down for a second. So here it is in words. The population mean height for females at UNM eligible to take our statistics class, right? I'm trying to think of who the population is. It seems that our population isn't the sample of students in our class. It's something larger. It's all students who could be taking our class. And I'm treating our class as a sample from that larger population. So is that mean height different from the U.S. population value of 64 inches? And I've specified here mu naught equals 64. In notation, the null hypothesis, H naught, right? So I think I described this in the video, but if you've ever been to England and played tic-tac-toe, they call it noughts and crosses. A knot, they just N-A-U-G-H-T, naught is another word for 0. So that's why it's called H naught rather than H0. Anyway, H naught is that population of females at UNM equal to 64 inches versus the alternative we're looking at different from, and so that is not equals. Okay, it could be greater, it could be less. We're not choosing a side, so we're saying not equal. Part 2, we're going to let alpha equals 0.05, and that is the significance level of the test, and which is also equal to the type 1 error probability of if the null hypothesis is true, that we incorrectly say that the null hypothesis is false. The test statistic is from above. So let's go look at the code now, where we will get the t-statistic and the p-value. Okay, so we've got our hand data. We've filtering just for females, and we're using the column height in inches. So we're pulling the data out for that one column. That just gives us a string of numbers. If we put that, if we copy that into R down here, I think I probably need to set working directory, and I think I'll just run all, and then I'll just run that piece of code. Okay. So this command started with the hand hand data, filtered it by females, and pulled out the heights. And so this just gave me a vector or a list of numbers. All right. So we're using that list of numbers. Then the true, or the hypothesized mean is 64 inches, and the alternative is two-sided. Two-sided corresponds to, oops, I need to scroll down. Two-sided means that the alternative is not equal to. And in RStudio, if you look at the help for t.test, you'll see that the options there for the alternatives are either two-sided, less than, or greater than. Okay, and so you want to use those words in quotes to identify which direction the alternative hypothesis goes in. All right, the result goes into t_summary, and I did _f for females, and here are the results. It shows what the data, how we got the data in there. It gives us our t-statistic, that's the thing that we care about, and it gives us our p-value, the other thing we care about. The degrees of freedom is based on the sample size, and it is adjusted for the number of parameters that we needed to estimate after estimating the mean and the standard deviation from our sample to get our t-statistic. It's to always check this alternative. True mean is not equal to 64. Okay, so that corresponds to specifying two-sided. Okay, it might also say less than or greater than here. It has a confidence interval, which is what we looked at last time, and the estimated mean. So this t-statistic and the p-value is what we're going to use to make our decision. So let's scroll down and use that, and then we'll come back and look at that plot. So here's a t-statistic, 5.2. Here's the p-value. Now 9.35 times 10 to the negative 7. That means that there's 6 zeros before this 9. So this is 0.000009. Okay, so that's the observed significance of the test. Is that less than 0.05? Is that less than alpha? It certainly is. And so based on our rule, if I page up for a second. Okay. If the p-value is less than alpha, then we reject the null in favor of the alternative. Okay, so now I'll page back down. Because the p-value is less than alpha, we have sufficient evidence to reject the null hypothesis. And now we can state what our conclusion is in words. What does it mean to decide in favor of the alternative? We conclude that the observed mean height is different than the U.S. population mean. Okay, that's almost everything. I'm going to look at one more thing. I did write this code where I can plot the p-value effectively for a test. Unfortunately, when you've got large t-statistics, like this one is 5.2, once you get a t-statistic sort of beyond 2.5 or so, it's hard to view it in the t-distribution, because the p-value is the shaded area under this t-distribution curve in the direction of the alternative. In this case, the alternative was not equals, and so that is a two-sided test. So let's see. Oh, here we go. The t-statistic is 5.2, so we've got a 5.2 over here, and so the area under the curve from here out to positive infinity is shaded. You can't see it because it's below the curve, or, you know, the curve is too flat over here. And also to the left of negative 5.2. That's the t-statistic, okay? So that shaded area, that's the part that's shaded. And it tells us here that the p-value is 9.3 times 10 to the negative 7. It is nice to see an example where the curve is not so flat. One way to do that would be to, let me just do an example in the, let's choose a mean that's closer to the actual mean height. So let's see, our observed mean was 65, so let's do that number instead. I'm going to copy this down here. Okay, so this is just for demonstration purposes for us. Okay, if instead of 64 inches, we were wondering if females were a different height than 65 inches, then our t-statistic then would only be one standard error away from the mean, the population mean. So our t-statistic is 1, and now you can see that greater than 1 and less than negative 1 is shaded, and that shaded area is about 0.3. So the plot can show something when we have t-statistics that aren't really large. Okay, so with that example, now it's your turn to test the male height, and in this case I've specified greater, and so you'll need to modify the statements to correspond to the hypothesis that you wish to test. So there's two things in here to change. I've got my data set up for you. I've chosen males. The mu is something that you'll need to specify, and the alternative. Okay, so based on, so let's page up for a second to the true values. Here is the value of males from the US population, 69.5. So you'll need to, for the males, you need to specify that number here, and also you need to change the alternative to be greater than. And as we saw in the help, the alternative needs to be, quote, greater. Okay, so if you make those two changes to this code, then you will get a test here that is correct. Right here in this example where the mean is not equal to 0, that is not what we care about. We know that men are taller than 0. And this plot will look much better as well. Okay, and then you just fill everything in here. I don't think I have that much to say, actually. I think you can do this. So go ahead and make your statement in terms of the students in our statistics class being taller, or the mean being greater than the US population, and specify those down here as well. And then fill in the t-statistic, fill in the p-value, make your conclusion based on whether men are taller or shorter, or whether or not the p-value is less than or greater than alpha. And I've got one more piece here, and this is usually the hard part. So we have made a conclusion, and I'll go up to the female example in a moment to discuss this. So given your conclusion, state whether you could have made a type 1 error or a type 2 error, and why it is one but not the other. Okay, so you'll recall, I should probably just do this from my lecture notes. Okay, this table is pretty good. I think I have a similar table in my lecture notes. Okay, so what type of error you could make depends on what decision you made about the null hypothesis. Okay, so the way this table works is columns are the state of nature. It's what is actually true out there. It's the true state of nature that we don't know. So either the null hypothesis is true, for example, women in our class are on average are 64 inches tall. That would be a true null hypothesis, or it's false. They're not that tall, or they're taller. Okay, they're not equal. Their mean is not equal to 64. Okay, so that's the true state. That's what we're trying to make a decision about. Over here is what decision we actually make about that null hypothesis. And we can either fail to reject the null, or we can reject it. In our female height example, we rejected the null. Now, if we rejected the null and the null was false, then we made a correct decision. That's great. But if we reject it and it turned out that the null was actually true, then based on our rejection, we could have made a type 1 error. Okay, so basically, when you reject it, one of these two things could have really happened. We either made a type 1 error if we made the wrong decision, or we made the right decision and we were correct. So that gives us our type 1 error if we reject. But if we don't reject, if basically our data are consistent with the null, and the null is true, then we make correct inference. But if our data was consistent with the null, but the null happened to be false, then that's where we could have made a type 2 error. That we should have rejected that null, but we didn't have enough evidence to reject it. Okay, so that is how to answer. Oh, I don't know why it resized. That is how to answer this question. Given your conclusion, state whether you could have made a type 1 or type 2 error. It depends on whether you rejected or failed to reject. All right, next example, the Earth's water example. So we want to answer, we're basically going to do a hypothesis test. And the question we want to answer is, conduct a hypothesis test to determine, that looks a little small to me. Conduct a hypothesis test to determine whether the proportion of water on the beach ball is different from the amount of water on the Earth's surface. So in this case, we're sampling from the outside of a single beach ball. We're tossing it around, people are measuring it. And we want to know whether that beach ball's proportion is different from the true number. So different from means we've got a two-tailed test, and the proportion that we're testing is 71%. All right, so we created this little table and of our data, and here is our binomial test. We've got x, let's see, well, x is the number of successes, n is the total number of trials. So in the binomial test, we've got x is 21, the number of successes, the output is down here. The number of trials was 35, and I'm specifying a confidence level of 95%. That's I think that if you don't specify that, it doesn't give you a confidence interval. We actually don't care about the confidence interval in this class or in this assignment. We just care about the hypothesis test. Okay, and that all goes into B summary, and our exact binomial test gives us a p-value equal to 0.31. Now, you might be looking for a test statistic here. For an exact test, we don't really have one except for the data themselves, 21 out of 35. So we will probably report those as our test statistic. If we had done a proportion test, prop.test, then we would have a test statistic that would be a z statistic, and I discussed those in the notes. Okay, now this test isn't quite right yet. Okay, notice that the alternative hypothesis down here says the true probability of success is not equal to 0.5. Well, we don't care about 0.5. We care about 71%, 0.71. So that is something to modify. Let's take a look at how to do that. So if I look at the help for binom test, you can see in the binom test in the upper right I've got x, I've got n, and then I've got p equals. That is the hypothesized probability of success. That's where we want to put 0.71. Okay, so if I were to rerun this and put p equals 0.71, don't worry about those warnings. That's from something else. Okay. Then we've got here we've got the true probability is not equal to 0.71. Great, and there's our p-value, 0.19. So that's what you should have for yours. We've got this plot, which we discussed in the last video, and then we've got the hypothesis test. So go ahead and state your hypothesis. This time, you can follow an example from the notes as well. We're not looking at a population mean, but we're looking at a population proportion. And the population we're looking at is the population of the plastic on the beach ball. That's our population. Is the true proportion of water on this beach ball equal to, or is it not equal to 0.71? And you can specify those in notation down here as well. You'll put in p equals 0.71 and p not equal 0.71. Now the code for that, why don't we take a quick look at how we did not equal to, because there's a little bit of typesetting here to do. I'm finding the example. Okay, here we go. So here is the mean height for females. And in LaTeX and also Markdown, we can typeset equations delimited by $signs. Okay, so /mu is mu, the Greek letter mu, and over here I've got also mu /ne for not equals 64. So that gives me the not equals symbol. So if I was you, I would come up here and just copy this, and then in place of mu, put the letter P, and then put 0.71, and same thing over here. And that will give you your equations to fill in this spot right here. Okay, alpha equals 0.05, that's good. In this case, we don't really have a z statistic because I used the binomial test. You could use a prop test and get a, but I would just maybe say here that the test statistics are x equals 21 and n equals 35, the number of successes and the number of trials. We've got the p-value, we've got our conclusion because the p-value equals, is greater than or less than alpha, whether we reject or fail to reject. And our conclusion, therefore the beach ball is consistent with the amount of water on Earth, or it's different from the amount of water on Earth, and then whether or not you could have made a type 1 or type 2 error based on your conclusion. So, for example, if you didn't reject, then you could have made a correct inference, or you could have committed a type 2 error. All right, last one. You guys hanging in there? Okay, African countries. So in the UN. So I discussed the example in the last video. We basically gave a priming number to students and asked them to make a guess as to whether the number of countries in the UN was greater or less than this random number, either 10 or 65, and then to give their best guess as to the percentage of countries in the UN that are from Africa. And the data look like that, where when we primed them with the number 10, they guessed lower numbers than when we primed them with 65. So we influenced their guess based on a random number not associated with the problem at all. So what we want to know is, we've got two samples now. We've got a sample of people who experienced the condition number 10, and we have another condition, 65, that a separate set of students experienced. And we want to know, are these two means different from each other? Now by eye, this is a pretty big difference, but we want to answer this question statistically. So, a priori, before we observed the data, we hypothesized that those who were primed with the larger number would provide a higher percentage than those with the lower number. Okay, so this is a one-sided test. So I've got the code here for a t-test, and in this case we've got two groups. This is our two-sample test, and we've got our response variable, the UN percentages, tilde the priming number. So what is the percentage conditioned on? It's conditioned on the priming number. So the priming numbers define our groups, our two groups. And our alternative is less. And what we need to do is, after we get that result and report it, we need to double check the order that the groups appear in the output to determine what alternative to use. In this case, the group the group for the priming number 10 was reported first, and then the mean for 65 was reported second. And so if we put a less than sign in here, that would say the group 10 its mean should be less than the group 65, and that's consistent with what our hypothesis was, that 65 was greater than those with number 10. Okay, so this less than is the correct order. It is possible, and it's bit me before, to do this t-test and to specify less than, and then for these groups to be ordered in the opposite way than you expected, and then you're going in the wrong direction. Okay, so we've got a t-statistic here of almost -3. We have a p-value of 0.002, which is pretty small, and this true difference in means is less than 0. Now it is possible in a two-sample test not to just ask whether one is less than the other, but it's also possible to ask that one is less than 5 less than the other. You know what I mean? Like a group 10 is less than, hold on a second, the autocorrect is killing me. The mean for group 10, is that less than the mean for group 65 minus 10? So you could have an offset that you want to know whether, anyway. think I've said it enough times now. All right, here is, oh, we can see, you see that itty bitty triangle down there? That's the area under the curve that we're looking at. The t-statistic was almost -3, and the tail is less than, so it's heading off to the left side. It doesn't appear on the right side, and that shaded area is 0.002. Very, very small. Okay, and so now you just state the hypothesis in words and notation, just as I have in the notes for a two-sample test. We've got our t-statistic, we've got our p-value, and I'm not quite sure. So you can see that the dollar signs are showing up here. All those should be typeset the way the first example was, way up here, where there's no dollar signs. Instead it looks like equations. Well, hopefully that will work out for you. But something changed right here. You know what, I'm going to take just a second and see if I can identify the weird thing that happened between the female example and the male example. Usually it's just like a hanging dollar sign somewhere, but I don't see an issue anywhere. Hopefully after you fill some of these in, it will knit correctly. So anyway, that is the end of this assignment video, and I hope that this gives you some good, meaningful practice with interpreting, setting up and interpreting hypothesis tests.